Oh, okay. All right. Sorry about that. We got this. Of course, when I'm already running late, that's when the batteries are dead on the mic, and I got to do that too. But let's do this. So we want to finish our conversation about OAuth 2.0 today. There's a lot of details, a lot of stuff that goes into this. And if there are any questions, make sure you're asking them now, because Monday we're moving on. We got to move to image uploads and homework 3 content. So let's wrap up some OAuth. We got to just the beginning of step 6, but let's back up to step 5. Halfway through step 5 a little bit, just to refresh where we're at. We already went through the whole authorization request and grant process. So we have an authorization code that we're trying to trade in for an access token, and the API needs to verify that we are who we say we are. They need to authenticate our client to make sure that this is a legitimate transaction, and they need to verify the user through the authentication or the authorization code. If we have this authorization code, then they're going to be happy with us. So when we send this authorization grant to the server to trade it in for a token, we're going to set the grant type. This is part of the protocol, part of the RFC, a grant underscore type, all lowercase, and that's going to be set to authorization code to say that I'm trading in an authorization code. We're going to send this to the token endpoint, so the API knows we're trying to get an access token, and the way we're getting that access token is by giving it an authorization code. So the server can support any number of ways to, not any number, but a lot of different ways to be able to get an access token. We're using the authorization code flow, so we have to let them know that we're using the authorization code flow and that this request contains one of those codes. We're also going to provide the redirect URI that we used during the initial step for reasons. I'll leave it at that. But we need to provide this again. The server will use this to verify that this is a legitimate transaction, even though we already registered the redirect URI and sent the redirect URI on the authorization request. They're going to ask to see it again. It's part of the RFC. We have to send it here. So even though we already verified it, they're going to ask for it again. And we're going to send it to them again. We're going to happily oblige. We're going to comply with that. And we're going to send all of this as the content of our post request. Remember, we don't have to use redirects at this point. We're not going through the user as an intermediary. We're talking directly to the API. So we can send them a post request with any structure, any format that we want. So we're going to send a post request with all of this information as the content of the request. And we can use any format that we want. Depending on the API, it's whatever they want to use for this to be able to communicate this information. Spotify, for what it's worth, uses URL encoding. So we're going to build effectively what would be our query string, but we're going to put it in the body of a post request instead of in the URL. So we're still using our percent encoding, our URL encoding, but all we're doing is giving an authorization code, which for Spotify's use case and this should be true anywhere you go, isn't going to contain any special characters that need to be percent encoded anyway. So something we don't really have to worry about. We're going to slap that code in the request. The redirect URI still has to be percent encoded, but we've already done that. We already had to do that one time, and it's the same exact string, so no worries there. And then the grant type of authorization code, no percent encoding there either. So we don't have to do any extra percent encoding that we haven't already done. So it's not that big of a deal that it's URL encoded, that it's URL content. But we need to make sure we have our content type. Since it is URL encoded, we have to make sure our content type says, hey, this is URL encoded, or else it might get blocked at some point along the way. That might get rejected by the API. And we're going to send that to /token endpoint. I just mentioned this, but we're going to send that to the /token endpoint. This is part of the RFC. It says you're going to have an endpoint that is /token for your auth server, and this is where we're going to send these requests. We're going to send the authorization grant to be able to get an access token. That's the token endpoint. It's a general endpoint that gets any tokens, and we're using it for the authorization code flow, so we're going to access it with an authorization code. And then if everything checks out, the server is going to look at our client secret. I skipped that part today. We kind of went in the middle of 5, but that would be in the authorization header. Authorization basic, and then that base64 encoded client ID : client secret. It's going to use that to verify our identity because we're the only ones who should have that secret. Then it's going to use the code to make sure that this was a code that was given to the client. They're going to remember that they gave that code to this client. They're going to look it up in their database and make sure it's a legitimate code. So once the client and user are both verified, they're going to send us an access token. Obviously, if anything goes wrong with that process, something doesn't check out, the redirect URI isn't character for character exactly what they expect it to be, then they just say, try again, invalid code or whatever error message they want to send back to you. But if everything checks out, we're going to get a response that's going to be an access token. And the format for this is can vary by API. The RFC doesn't say this is how you're going to send the tokens back. And for what it's worth, Spotify, I don't have it on the slide here. Oh, yeah, it does. Spotify will use JSON for this. So your response from the server when you cache this in, you're giving it URL encoded parameters, and it's returning JSON. I don't know why it mixes formats like that. There might be a good reason somewhere along the way. But we're giving it URL encoded content, and we're getting back JSON content. So the response is a JSON object with an access token key. We're going to parse that JSON. We're going to parse that JSON, grab that access token, and then we're able to use that for our API access. Refresh token, topic for another lecture, but that lecture happens to be today, just the way the slides lined up because we were finishing up some slides from last time. Today we're going to talk about refresh token. So when we get this JSON object, we might have refresh token and access token both. And then we can make API accesses. We can access the API on behalf of our user now. So we can send requests as long as the request has our that access token that we got from the server that we got through this whole process. We send that access token to the server, and that's the only piece of information we're going to use to authenticate our API requests. We're going to send the access token. The API looks up in their database. Well, we'll talk about refresh tokens, and we'll change this a little bit. But what they can do is look up that token in their database and say, who is this? What is this token? Verify the token based on what they look up, see the user, see the app, get all the information about that, and then look at the scopes for that token, and then figure out, is this allowed access? Is this an authenticated access or not? Should we send back a 403 response, or is this cool? Should we send back a 200 with some private data and let them access all of their stuff? We're going to do that through the authorization header. Authorization bearer instead of basic. Bearer, we are the bearer of the token, is, for my understanding, what that means. We control this token. We possess it. So authorization bearer, space, and then whatever the token is, whatever that access token value actually is. Then based on the method and the path of the request, they're going to figure out what endpoint we're accessing. And maybe it's a post or a put, and there's a body of the request. But whatever the request is, this header needs to be there to be able to authorize that request. And we're using headers at two different points of time here. We're using the authorization header to authorize. We're putting some token in an authorization header. And last week, we used cookies for this. We put an auth token in a cookie, and then we sent a request, and that cookie was checked. And the cookies worked through headers, so it's kind of the same thing using cookies. So why are we using authorization headers here? And a big reason, for API access at least, we have to do it this way because we're going to be making requests for multiple clients. Our app is going to be making these requests to the server for any number of users. If we got 1 million users, we're going to be making requests for 1 million different people with 1 million different access tokens. So we can't set that as a cookie because it doesn't make sense to send that access token as a cookie and have that stored as a cookie because we don't want to send the same access token on every single request to this API. So cookies are off the table for these things. We can't use cookies for access tokens. Doesn't make sense to do that. So that's why we're using the header when we're making these requests. It lets us go to our database, pull whatever access token we need for this specific request, put it in the header, and send it just on that request. And the next time we make a request, it might be for another client, might even be for a different access token for the same client. We're going to pull that from our database, set it as the header, and then send that request on its way. We're not going to let the browser, there is no browser even, we're a server at this point. There's no browser at all to maintain the cookies, so we'd have to manually maintain the cookies anyway. Just doesn't make sense to use cookies at all for these exchanges. And finally, what we want to build in AO1 is login with. So login with Spotify, all the steps that we just went through, that's going to be true for any OAuth access, any OAuth anything, no matter what we're doing. So for AO1 and AO2, you're going through this whole process, regardless of what your use case is. And then if we're using login with specifically, now that we have access to the API on behalf of our user, we're allowed to access their private data based on the scopes that we asked for. So you make sure you're asking for the right scopes to get the information you want. And for our homework specifically, we want their email address. In general, you want some identifier to uniquely identify this user for this service. So we're going to pull their email to get that unique ID. So we're going to ask the API, hey, who is this user? Because notice at no point in this entire process so far do we have any information about the user at all. They clicked a button. That's all we know about them is that they went to our app and clicked a button. We might be able to check like our auth token. Maybe they're well, that doesn't make sense if it's login with. But we might have some information from our server itself, but we have no information about this user on this service. They clicked a button. They sent us a code that is completely cryptic, doesn't mean anything to us, but did not contain their username or anything, no information. They're not even claiming to be anyone specific on this API. And not until we get the access token, which again has no identifying information about the user, and then once we use that access token and ask for the right scopes to be able to ask for this information, can we go to the API and say, so who is this anyway? So we'll make a request, ask for their profile information that contains their email, and then get their email address. We finally get some private data for this user, get their email address, and some other information, but for our purposes in AO1, we just need their email address, and then create an account for them. Just like if they registered username and password, we're going to register them, but their username is going to be their Spotify email address, whatever email address they use to sign up for their Spotify account. We're going to use that email address as their username, and then they do not have a password. There's no password associated with this account. So make sure that no password matches this. I should have put that as a security thing in the homework, actually. There should be no password associated with this account, which is very different than a password of empty string. Don't let anybody log in as this user if they use a password. So they get no password, and then go through the login process. So this is the registration process, and then go through the login process, generate an auth token for them, set that as a cookie just like you would before, store a hash of that auth token in your database, do the same thing you would do to log in any other user. You're just registering them as their Spotify email address, and then no password ever should be valid. There's no password that anybody can type to log into this account, and then do their auth token as usual. When you see that auth token again, you're going to look up their record. You're going to see their email address. I skipped a step there. And you're also going to store, is it on the next slide maybe? You're also going to store their access token with their account. I think it's on the next slide. You're going to store their access token with their account too. So when you create their account, username is their email address, store their access token, store a hash of their auth token, and then set that auth token as their cookie so you can verify this user. When they come back, you can pull their profile. It should have their email address, which you're using as their username, and their access token so you can make extra requests to the API on their behalf. If they already have an account, so you look up that email address and they already have an account, then you're preserving that account, use their existing account, and update their auth token and their access token. And they shouldn't have to re-verify with the API on steps 2 and 3. That'll be an automatic redirect, and they'll just be logged back in. To them, it's just one button press and they're logged back in. So that's login with. The actual details, once we have API access on behalf of our user, the actual login with logistics is pretty straightforward. You ask the API for some private information, some identifying information, some PII, if you will, and then store that in our database for their account. Use that to fill in the details of their account, store their access token, and then everything else is just like regular login that we talked about last week with auth tokens. Bless you. And then when you want to access the API in their behalf, so whenever, for AO2, whenever somebody sends a chat message, and by the way, I mentioned this in the homework document itself, but if you're doing AO1, do AO2 as well. AO2 is almost no additional work on top of AO1. So once you go through this whole OAuth process, it took us 2 lectures to go through, well, more than 2 lectures now to go through. You go through all that process, finishing up AO2 is nothing. So for AO2, whenever this user sends a chat message, you have their auth token, hash it, look that up in your database, pull their account. If their account has an access token, then you know it's a Spotify user. Then go to the API, hit a different endpoint that gets their current playback information. Make sure during the authorization request you ask for the proper scope to be able to access that information. Get their playback. It's going to give you a big JSON object with all kinds of information. Find the title and artist of the song that's currently playing. If there is a song that's playing, there might not be a song playing, and you'll get a 204 no content. Is that 204? I think it is. You'll get a no content if nothing's playing, so make sure you're not trying to parse a no content body, an empty byte array, as a JSON string. You'll get a JSON decoding error every single time. I know because I did that in testing too many times, more times than I want to admit. But if it is not empty string, if there is an actual JSON string that was returned, parse it, look for the values you're looking for, grab those values, and then add that to their chat message so you know what they were listening to when they made that message. And you can't hash these tokens, so there is a big risk here. The tokens, when we talk about refresh tokens, this will be true. It's true for access tokens as well. We can't securely store these. We just can't do it. So these need to be as protected as we can get. Protect the database, but if your database is compromised, they have access to this API on behalf of the user. So a few things we can do to limit this. The big thing is don't ask for more scopes than you want. One, for a user experience, a good user experience, don't ask for too many scopes. But also, if your access tokens are compromised, don't let the attacker get more information than was necessary. Limit the amount of damage that they can do. It's still not good, but you know, let's do what we can at least. And we can't store hashes of these tokens specifically because the API needs to see the original tokens. Since they need to see the original tokens, we need to be able to know what the original token was. So if we only store a hash of that token, we can't go from that hash back to the original token to send to the API the value that they're expecting. So we can't just store hashes. Since we can't do a one-way function because we need to go the other way, it's not going to work. We could store them encrypted, but we do have to decrypt. We have to have the means to do that in our software, and that's another point of vulnerability for the attacker. They're going to get the decryption process, the decryption keys. We just can't securely store them in the same way that we can store passwords and our auth tokens. We can't do the same thing here. So you do store these in plain text. As much as it feels weird to do that, we store these in plain text. The access token and eventually the refresh tokens. So that's it. After the whole process, LO2 was like one slide. So make sure you do LO2. Nobody should be getting AO, I mean. Nobody should be getting one application objective on homework 2. You're either saying, man, this week was a lot, I'm not even trying, or you go through the process and you do both of them. I don't expect anyone to get just one of the two, because that'd be a waste. If you did all of AO1 and didn't do AO2, like, please grab that second AO. You definitely should get both of them if you're doing this whole thing. Don't do all that and only get one of them. So any questions on... I downloaded the other one, but I didn't open it, is what I did. So any questions on all of that? Bless you. Oh, that is a new message. I checked my Wi-Fi thinking it's broken. I was just ignoring chat. Is OAuth safe even when step 6 is compromised? Like someone steals the access token in the middle of the process, or is it safe because of HTTPS? If somebody steals the access token, they have access. That's not safe. It is protected by HTTPS. So when that access token is flying through the internet, God damn it. When that access token is flying through the internet, it's going to be encrypted through HTTPS. So it is protected through that. But if that token is compromised, and it's part of what we'll talk about in today's lecture proper, if that access token is compromised, the attacker has access. Like that's it. So if they can get your database, which can't protect the access token, not properly, like through hashing, it's game over. They got access. They have it. So there are dangers in this. There's places where we got to tread carefully when we're using OAuth 2.0. Reminder, I mean, we just kind of went through it, but reminder of what the authorization code flow is, these 8 steps. Well, really 6 steps to set everything up, and then the last 2 are actually using the API. So let's talk about a couple extra topics. These are like add-ons. For what it's worth, you can breathe easy a little bit today that none of today's content is required on the homework, and it won't be on the project either. But these are extra topics that, since we're talking about OAuth, we got to talk about some of these extra things that you will encounter, like state, for example. I say explicitly on the homework, you don't have to use state, you don't have to use that. But in the Spotify API, in the documentation, it says strongly recommended that you use state. So let's talk about why that's strongly recommended. Even though I'm not explicitly requiring you to do it on the homework, honestly, there's so many steps already. It was over 2 lectures, 2.5 lectures to cover all the steps. Anything that was optional, I was cutting out of that thing. But I still want to talk about them. I'd be doing a disservice if we didn't at least talk about why that exists. So let's talk about it. And talk about attacks. Mostly today, I should call today security, because we're going to talk about attacks. So we have a cross-site request forgery attack that can be launched on the authorization request process. So instead of our app initiating the whole process through the user clicking a button, what a clever attacker is going to do, and this attack is pretty clever in my opinion. There's a lot going on with it. But what instead, the attacker is going to initiate the process. They go to our site, they click the button, they grab the request, they can look at our client ID and the redirect URI. So they know exactly how to structure a valid request. And what they're going to do is either legitimately by clicking the button on our app, or just looking at all the information and handcrafting their own request to the API, they're going to initiate the process of an authorization request for our app. So it's our app, our client ID, the app that they're targeting, our redirect URI, but their credentials. So they're going to go to the third-party API, use their account, and generate an authorization grant. So they get an authorization grant for their account. To the API, this looks like the attacker clicked the button on our site, was redirected to them. Everything is legit. It's 100% legit. It's a legit request with the attacker's account. The attacker is going to get the redirect URI and redirect the attacker to our app, but the attacker is going to say, nah, let's not do that redirect. Instead, they're going to grab that redirect URI with the query string that contains the authorization code. They're going to grab that redirect and put it in their pocket. They're just going to save that for like right now. This is all going to be initiated as soon as they find a victim. And then they're going to get the victim to click a link. So they send the victim an email, free Bitcoin or whatever. This is Microsoft support. Click this link to reset your password, whatever it is. And bonus points for them if the link is something to do with your app. So whatever they're trying to attack, like click here to just go to the app. Maybe it's just a link that says your app or whatever. But this link has their redirect URL, the redirect containing the authorization code, the attacker's authorization code. They put that redirect URI in the link. So the user clicks a button from the attacker, and clicking that button should initiate the whole process so that authorization code isn't expired by the time the attack happens. And then the user is redirected to our app. And now we got the user to click a link. There's no same origin policy that's going to protect us here because this whole process is made off of third-party requests. So same origin policy, anything we talked about before, not going to protect us here. Somebody clicks that link, they're falling for this. They're kind of screwed. So they get redirected to our app, and to the user, they're just looking at our app. They don't know anything happened. They never saw the attack site. They clicked a link that, if the attacker's smart, said, go to this cc312.com or whatever. And they're looking at your app, and they don't even know anything happened. They're absolutely clueless to what just happened. They clicked a link from somebody else, somebody in a forum or something, put a link, click here or whatever. They click that link, and this is what happens. This is where they go. And your app isn't going to care that this was sent through a link and not through a 302 redirect, by the way. How's it even going to know? It doesn't know. So anyway, the app gets this request with an authorization code, and here's where it starts to get scary. This authorization grant is linked to the attacker's account, but it was sent by this user. What our app is going to do is it's going to do its thing. It's going to do its usual thing. Your endpoint is listening for requests on this redirect URI. It's not going to check HTTP stateless, so it's not going to check if it did initiate an authorization request. It's going to say, oh, when I get a request on this endpoint, I'm going to treat this user as the one sending me this grant, and I have some obscure code which has no information about anybody on it. I just know I got a request containing an authorization code, so I'm going to do my thing. My thing is to cache this grant in for an access token, and then I'm going to link that to the person who sent it to me, because who else am I going to link it to? I have no other information at this point until I access the API and start getting some information. So I'm going to link this token, this access token, to the user who sent me the authorization grant. Because who else would I assign it to? Why would I do anything else, right? Why would the app do anything else? We're either going to create an account, update an account, or, whatever, and then we're going to give an authentication token as a cookie to this person. This is the person. If this was like a login with request, ideally for the attacker, this is a service that the user already uses, and they're going to get a fresh access token assigned to their account that already exists. So we just associated this access token to this user through an authentication token, and now whenever this user visits the site, we're going to look up that auth token, the hash of the auth token, and pull up that user's account, which is going to contain an access token to this third-party API, but that access token is linked to the attacker's account. And that's where things get scary. Now this user is happily using your app, completely unknowingly interacting with the attacker's account on the third-party site. So if this is a bank, if the third party is a bank, for example, and I deposit money, I just deposited that money into the attacker's account. If I send any private information, in general, any private information that this user sends to our app and says, hey, send this to the third-party API on my behalf, it's being sent to the attacker's account instead. So the attacker, as this user is using our app, this attacker is looking at their account on the third-party app, and seeing all their activity, all their private information, whatever they're sending, this person gets to see all of that information, which is bad. Maybe it's their Google Drive. They're seeing all the files that they upload to Google Drive because they're actually uploading their files to the attacker's Google Drive. Bad, very bad stuff. So we want to prevent against this. We're going to do that with state. This is where state finally comes in. We're going to get rid of that attacker with this one simple change to what we're doing. We're going to add a state parameter to the initial authorization request. This state can be anything, some long random string, something unique to this user's request. And this is behaving very similar to our cross-site request forgery tokens, our same prevention from cross-site before. Very similar to that, we're going to generate a random value and associate it with this user. And then we're going to send that user, I got to say this. The RFC does recommend, they don't say anything that what the state has to be, but they do recommend that it's a hash of the user's state. So whatever, I say auth token here, but they shouldn't have an auth token if the application is logging in with. That would be if they're using the API with their account that they already have created on our app. But some hash of their cookie that we're using to track them as a guest, tracking their session, a hash of that would be the ultimate security, because we can verify that this was associated with this client, even when they don't have an account in our database. So something that can uniquely identify this user, even if they don't already have an account, because if they're logging in with, they don't have an account yet. So we have nothing in the database to look up. So, but anyway, some random state that we're going to associate with this user. User goes through the process. The API will support this state thing. And when we get the authorization grant, they're going to give us that same exact state back. Now we can verify, did we get the same state back from this request? And was it the state that we gave this user? If we're using cookies to track this user, we can make sure, is this the hash of that token, or is it just a random value and I have another way of verifying that I gave this value to this specific user? So this is going to completely prevent our cross-site attack, because when the attacker does this, the attacker is using a state that our app issued to them, or possibly any state that they ever came up with. If they want to try to reverse engineer how we're generating our states, they can try to do that and try to guess what we would assign to the state for this user that they're trying to attack. So we do have to be careful about exactly how we generate our states. If they're predictable, they're not doing their job. But if we give a random token as a session key to this user, and then a hash of that token is our state, the user would have to attack that session token, which if we're protecting our cookies, there's a lot to it, but some way that the attacker's not going to be able to guess that state. Now this authorization grant is going to have the state of this attacker, which won't match this user, and we can reject it outright right there. So the attacker can't get their authorization code into this user's redirect URI because it won't match the state that we gave this attacker or that the attacker guessed when they sent their authorization request to the server. So state, in short, the TLDR, the state is going to protect against cross-site request forgery attacks during the authorization grant process. Would the state of the user that makes the hash be their IP or something? What if they guess right? If they guess right, then they can launch this attack. If it's a hash of their IP and the attacker knows that's what you're using, then the attacker has the task of finding the user's IP address, which isn't that hard of a task. If they're running a server and they get a request from you, they have your IP address already. So if they get you to click a link, instead of that link being directly to your app, they're going to have that, which, by the way, that link wouldn't even seem that shady. It's going to be directly to our app. But instead, if it's a hash of their IP, that link has to go to the attacker site, which returns a redirect containing a hash of their IP address, because once the user goes to their server has their IP address, because they have to, because that's how the internet works. That's how those IP packets made it to that server, so they have access to that information. So I wouldn't use a hash of an IP address. Okay, refresh tokens. So it's common, and you'll see this in pretty much any OAuth setup. Not all of them, but the Spotify one does. In your homework, I don't know if I say it explicitly, but you can flat out ignore the refresh tokens. I did say this before, I wanted to require them, but the access tokens last for an hour before you need the refresh token, and I'm not going to have my TA sit there for an hour for every single submission that they're grading to let the token expire, and then the logistics on the grading side are just a pain. So I'd have to have them look through your code and just kind of say, yeah, that looks like it would work, and that's just not how we're going to do the grading. So I want refresh tokens to be required, but there's just no practical way to do that. But anyway, this is a common way that you'll use these APIs. When you actually use OAuth APIs out there in the real world, you're going to use them for more than an hour. My playback for music that starts and stops and starts at the beginning and end of lecture, that has to run for more than an hour, so I have to do refresh tokens. But this is what they are and how they work. So in addition to the access token, the API will also issue a refresh token, and the access token will expire in some short amount of time. And when that token expires, you have to go back to the API with the refresh token and show them the refresh token. We don't cache in the refresh token, but we're going to show them the refresh token and use that to obtain a new access token, and optionally, I've never seen this in practice, but optionally a new refresh token as well, assuming if the API presumably if the API detects that there was some compromise of a refresh token, that it might issue a new refresh token as well. And this doesn't make sense if the authentication server and the resource server are the same server. If they're the same server, you really get almost no benefit from refresh tokens. So this is almost exclusively beneficial when these are actually two different servers. So this is the one point where I'm going to separate auth server and resource server and talk about the difference between the two. When these are split into two, the authentication server is responsible for authentication, of course. It's going to handle any issuing of tokens, refresh tokens, access tokens, getting the authorization grants, issuing the authorization grants, getting the authorization requests. All of that is going to be the auth server, and the resource server is only responsible for the actual resources that we want to access. The API endpoints that we're ultimately interested in, that's the only thing the resource server is responsible for. So only when we're using the API do we use the resource server. Everything else is the authentication server. When this is the case, we have a few advantages of using refresh tokens. So the refresh token is never sent to the resource server. And the assumption here is that, which I don't necessarily agree with, but the assumption here is that the refresh token and the accesses to the resource server, that these communications are more easily compromised than these communications. Not quite sure I agree with that, but that is part of the design here. Part of it, I will concede to, is that there might be a lot more requests to the resource server. You might be making like X requests per second. It might be a lot of requests. Whereas these requests, this refresh token cache-in, might be one per hour if it's Spotify's case where the token's expiring in an hour. So there are more communications. So just in that sense, maybe it's more vulnerable, I guess. I'll give them that much. But if this is compromised, then the attacker has that limited window. The token's good for an hour. If they attacked it right away, they have 1 hour to use that access token to do whatever attacks they want, which admittedly is a lot of time for an attacker, to do whatever attacks they want. And then after that, that token is invalid. The app is going to not cache in, but get a new access token using the refresh token, and the attacker's stuck with an access token that's invalid, it expired, and they have to try to attack another access token and keep launching more and more attacks. So it does limit the damage. They still can do damage, but we do limit the damage they can do if they compromise one of these access tokens. And there's performance issues. This one I'm a little more sold on. Not entirely sold, but I'm a little more sold on this one. Refresh tokens are faster. So this gives us an advantage in that the resource server, how do I want to word this? If we're not using refresh tokens, if we're only using access tokens, and access tokens are long-lived, whenever we access the resource server, what the resource server has to do is talk to the authentication server and say, hey, is this a legitimate token, or is this a token that's been revoked? With a short-lived token, we don't care if it's been revoked. Well, we really should, but we don't in OAuth 2.0. We're not going to care if it's been revoked. There's no mechanism to revoke an access token, but if we have a long-lived token that lives for days, years, then we want to go to some place to verify, has this token been revoked, because we don't want to keep respecting a compromised token. So we would have to go to the auth token with an HTTP request, because we're across machines here. The auth server has to look up in its database and see if this token is still valid, and then respond to the HTTP request with the answer and say, yeah, it's valid, and then the resource server can go to its database and do its thing. This is going to slow things down, especially when this is multiple requests per second that we're making. We can get a lot of API accesses, and we don't want to slow things down. We don't want to take this performance hit. So with refresh tokens and short-lived access tokens, what we can do is make the access token self-contained, so that the resource server has no need to check with the authentication server whether this token is valid or not, because if it is compromised, we're going to say, well, it's going to expire soon anyway, and we're going to live with that. But we're going to get this performance increase by being able to look at the token. It's self-contained. The resource server checks the token. It should be signed, hopefully at least, by the authentication server, so only it can verify. It's going to check the validity, and if it's a valid key, then it's going to respect the request. No HTTP requests, no database lookups to authenticate the token. It's all completely self-contained. And once it's self-contained, then no communication, I already said that. No database lookups, no HTTP. It checks the token, see if it's valid, and then accesses the resources. So it's a lot faster because we don't have to talk to the auth server, and we don't have to talk to a database. Another option would be to have a shared database to get rid of the HTTP request, but the resource server would still have to go to the database, verify the token, then go to the database for whatever resource is being asked for. And we got 2 database lookups for 1 request. We can cut that in half. That's going to be a pretty good performance increase. Whenever we go to DIS, you learn this in 341 if you've taken that already. Whenever we go to DIS, it's a very slow operation. Database by nature does have to go to DIS. Very slow. If we can cut database accesses and DIS accesses in half, that's going to give us a pretty good performance boost. So we do get a good performance boost because we can make these tokens self-contained and cut the auth server out of the picture when we're accessing specific resources. So this one I'm more so on. This is more of the benefit of refresh tokens, is a pretty big performance increase. But we do also get that security increase that we talked about here, that if we can protect the refresh token better than we can protect the access token, which again I'm not too sold on that one. But if we can, then it gives us extra security as well. So refresh tokens are pretty cool, and you're going to use them. It's just how most of these APIs work. They're going to work with refresh tokens. So you just have to get used to it. Even though it's a little harder to code, it's more work that you have to code on your app. We're going to do it because that's the way things work. So if we have an access token compromise, just to run down what our compromises are. If our access token is compromised, well, we say, okay, attacker, you get whatever scopes we asked for that token, but it's going to expire soon. This isn't the best security, but hey, we do limit the damage and the amount of time they can use it. But access tokens, pretty bad if these get compromised. And there's no way, if they're self-contained, there's no way to revoke these things. We can't revoke them because they're self-contained. If you have the token, you have access, period. How are you going to revoke it if there's no database lookup to check if it's been revoked or not? Can't do it. If a refresh token is compromised, it's actually not that big of a deal. If a refresh token is compromised, whenever you use a refresh token to get a new access token, you need the client secret. If you don't have the client secret, that refresh token is garbage to you. It doesn't do anything for you. So compromise your refresh token, it's whatever. Compromising a client secret, this is pretty bad, of course, especially if they get the refresh tokens and the secret. Now they can do pretty much whatever they want, except they don't have access to your redirect URI, so they can't go through the whole OAuth process. But any users who are already authorized to use the API, those can be compromised. And countermeasure to this, reset your client secret. Any good OAuth API is going to have some button like this where you can get rid of your client secret, get a new one, update your server to use the new secret, and now that attacker, that compromised secret is just wiped away, it's invalid, it's revoked. The API will know in their database, they look up that client secret, and they say, no, this secret's been revoked, what are you trying to do? And they won't be able to get anything there. And the API can also revoke this. If they think our app is up to shady things, they're going to, 49, where's my music? Oh, what the hell? Sorry about that. If they think we're up to shady things, they're going to revoke our... Oh, that's not the lecture question. There we go. They're going to revoke our access too. Where's the music?